All right, this week we're going to look at standard heats of formation. And so for that, we are looking at how to use Hess's law to figure out the heat of reaction based on the formation of the reactants and products and then combining them mathematically. So we're familiarized ourselves already with the notations. So we use the subscripts to symbolize the type of change: combustion, freezing, reaction, formation, all those kinds of things. So in this example, we have water going from the liquid state to the gaseous state. Right? So that's the process of vaporization. And so the enthalpy change of vaporization, delta H VAP, is equal to 40.8 kilojoules. If we look at the relative orders of the different chemical and physical and nuclear processes, we find that there's a definite pattern in terms of the magnitude, and we find that physical changes generally take the least amount of energy, and chemical changes a fair bit more, and then nuclear reactions far more than that. All right, so how do we use standard heats of formation? We use the subscript F. And then we use a little superscript 0 when it's a standard enthalpy, that is under normal conditions, standard conditions, and we're talking about 1 mole of the substance. So the heat of formation then under standard conditions, that is 1 atmosphere and 25 degrees Celsius, it's more like standard ambient. ATP and STP combinations, but with when we're talking about heat, we do use 1 atmosphere, so 101.3 kilopascals. If we're dealing with an element, well, an element is already an element, so because by definition the heat of formation is always the formation of the compound from its elements, we don't need to worry about the heat of formation of the element. So that's always given as a value of 0. So if we have this example for the heat of formation for water, water is made up of hydrogen, oxygen to give us the water, and then the delta H then for this is simply negative 285.8 kilojoules per mole. If we were to write it as or with the equation, it's generally given in this form, with a semicolon after the reaction, and then delta H naught F at minus 285.8 kilojoules. The 0, that's quite often as a superscript behind the H above the F, that's sometimes left out if we're already dealing with 1 mole of the substance. So this particular value is for this reaction equation the way it's written. So if we already have the 1 there, we don't necessarily have to have the 0 here, although it is implied in this particular case. Okay. All right. In general, though, heats of formation are usually given as a per mole value. Okay. So the heat of formation then for acetylene, for example, is at plus 226.75 kilojoules. And it's written this way. Third example then for the formation of sodium bicarbonate, written out in this fashion for 1 mole. Okay, it's negative 947.7 kilojoules. Okay, so that's the standard way of kind of getting this information. So how do we use heats of formation to explain heats of reaction? Well, we use a version of Hess's law. And we can use it by summing, or the summation of the heats of formation of all the reactants and products and combining them mathematically. If we use an example, what's the heat of reaction for the combustion of ethanol? C2H5OH. The balanced chemical reaction is written as such. And so what we need to do then is we need to first of all determine the heats of reactions of the formation of each of the products in the reactants, and then rearrange the heats of formation equations so that products and reactants are the same as the target equation. So that's the kind of standard way of using Hess's law. And there is a quicker and a little bit easier way of doing that. And well, one question that does come up is where do we get these values? There's a partial table in your textbook on page 318, table 5.5, that has some of these values that you might be able to use. All right, this equation is essentially Hess's law set up specifically for this type of purpose. And the way this is written out is that the heat of reaction, standard heat of reaction, is the sum of the enthalpies of formation of all the products, multiplied by, obviously, their respective number of moles, minus the summation of the heats of formation of all the reactants. All right, so the symbols that you may not have seen before, the big sigma is just the sum of, and the n values then represent the stoichiometric coefficients that are in front of each of the reactants and products in the reaction equation. All right, so that's what it looks like. Let's go back to our example that I mentioned here. So this is the reaction that we're looking at. We'll remember that heats of formation for elements are 0, so we don't actually have to worry about elements if they come up in our reaction equation. So these are our products, the carbon dioxide and the water. 2 moles of carbon dioxide, 3 moles of water, 1 mole will give us 1 mole of ethanol. All right, let's go through this again. Okay, so there's how we set up the equation. 2 moles of carbon dioxide times 2 moles times the heat of formation of the carbon dioxide, plus 3 moles times the heat of formation of the water. Sorry, my subscripts don't do subscripts. And then subtract the heat of formation of the methanol. Okay, so these values we can all get from that table on page 318. So then we'll plug them in. So 2 times the negative 393.2, 3 times the negative 241.9, and then subtract the negative 277.6. So summing these two, we get the negative 1,512.1 kilojoules per mole. Subtract the 277, and we get 1,234.5 kilojoules per mole. And so there's the homework. These questions are pretty straightforward. I don't think you should have too much trouble with these. The only catch is that they might ask you to do them according to Hess's law, where you have to actually set up those equations. But again, that shouldn't be really difficult at this point. Anyway, so a couple of questions. Try some of these. Again, you don't necessarily have to do them all, but do as many as you need to get comfortable with it.